So this talk is about programming intrinsic. This is essentially what we saw in this code just a few seconds in this assembly code. And do people actually have problems understanding assembly? Who does not completely has no clue about assembly? Is there anybody who? Yeah, I know that. But, so everybody has at least an idea what assembly is. It's a very, 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 very simple language that you can talk to a computer. Okay, so what we're going to do now is speaking about intrinsics. Intrinsics is a C version and a C-only version. So I, deliberately exclude all the Fortran users now, but you have to do it in C. It's not possible in Fortran. In case you need to use something like that in Fortran, you have to write it in C and then, for example, use the ISO-C bindings to actually import it into Fortran. Okay, so why should we actually bother? I mean, you always should know why you should bother because you're in it's high-performance computing, and if there is no other way of getting the performance, this is probably the way you want to go. Right? It's a little bit more complicated. It's also a pretty intriguing way. I like it. I like the way how this is done. Mr. Gilles here is one of the Intrinsics TGEM guys who has written very nice versions of that. So it's a little bit tricky, but it's very challenging and it's actually pretty cool. So why should we bother with intrinsics? I told you earlier on that there's very, very unlikely that we'll see any significantly higher frequencies in the processors in the coming years. Why? Because the power consumption goes quadratic with the frequency. So when I double the power for performance, when I double the frequency, I'll quadruple the power, which is what we can't do. We simply can't afford that. On the other hand, if I double the area, I just double the power consumption. And usually what Intel's production processors do, they shrink the size of the transistor, or the features, we call them, by half every 18 months. So every 18 months, we get half the size of the die. So if you would take a Pentium from 19, gosh, when was that? A long time ago, like say 20 years ago, then it would be, I don't know, yeah. So it would like minimize. It would just, basically, it wouldn't be present anymore. It's so small nowadays that it would be a minor feature on some of the chips. So usually we double the number of transistors every 18 months on a given area. So we assume that the transistors grow, as they always did, but the frequency will basically stay the same. However, not even the cores, so one would then assume that the number of cores doubles every 18 months, but that's also not true, right? So the number of cores doesn't seem to be doubled every 2 years. This doesn't seem to be possible. There are other technologies that they'll take more transistors, like branch prediction, like caches, and so on, that consume the transistors that were actually could be put into cores. So very likely, and the most efficient way of doing that, the performance improvements will come from vectorization. There's nothing else that can deliver that currently. Okay. So usually when you want to start intrinsics or vector intrinsics, and this is the only good way we use it for, apart from allocating memory, you come up with a problem like that. Why can't the compiler vectorize my code? You have a complicated piece of code. You can't write it differently. The compiler just doesn't want to understand it, or the implementation the compiler suggests is not sufficient for your use. Classical example is this type of matrix multiplication, where the compiler probably says, no, it's very inefficient to vectorize that. But we know that it is okay to vectorize, right? Because there is just basically, he would leave out an element here. Oh, it's a green vector nowadays. He would just leave a 0 element at the end. If he would write that, we would do it because we know we can put 4 doubles in such a vector. We know we would only use 3, but the compiler would still say it's inefficient. And we just recently, with a couple of workloads we're dealing with here at CSCS, we had exactly this problem, that vectorization, and Alfio was extremely working about that especially those small kind of loops will not vectorize or will not vectorize in the right manner. Intrinsics can help you. Okay, what are intrinsics? Intrinsics, they feel a little bit like library functions. They feel like any function you would call from any other subnet set or storage you have on your computer, like sinus or exponent, but they're just called differently, and they will exclusively deal with vectors. The intrinsics are directly understood by the compiler. It knows about these kind of functions, so they're not entering, they don't have to conform the normal C way because there is no type vector in C. We introduce that. Most intrinsics almost directly translate into assembly code. So behind each of these function calls, there is an assembly command. Sometimes there is a couple of assembly commands behind it, but it's usually very short code regions. There's not many of them. In order to use AVX Intrinsics, you must include a header. It's IMM Intrinsics, Intel, MM, I don't know what the MM stands for. We use MM for multimedia extensions originally, and that description stuck. So it's IMM Intrinsics, you include that, and then you can use intrinsics. Okay. Very briefly, the Intel64 Register Set. This stuff up here basically is a standard Intel processor, like any 64-bit processor. There are 8 registers that deal with particular necessities of the operating system and the core, basically pointing to an instruction pointer. This is where the instruction, well, the memory address of the current instruction is stuck in. There is 4 general purpose registers, RAX, RBX, RCX, and RDX, and there's a couple of others like a stack pointer, the base pointer, and so on. There is, there's not general purpose actually. They are pretty used in a pretty fixed way. Then there's 8 64-bit general purpose registers, R8 to R15, which you can just use for anything. You can write 64-bit information in there. 1 double, right? Or 1 long, stuff like that. Of course, you can also, underflow, say, use 32 bits of it by writing floats in it. And additionally, now on Sandy Bridge, there are 16 256-bit SIMD registers. And those SIMD registers, there's 4 doubles, space for 4 doubles in them, space for 8 floats in them. Or if you deal with 16-bit stuff, there's even more space. Right? Okay, we saw that before. This basically describes what happened to the vector lengths in the coming years. So in the generation before Sandy Bridge, we had 128-bit vector lengths. Nowadays, it's 256-bit, so it's 4 doubles or it's 8 floats. On Sandy Bridge, this is almost exclusively focused on floating point arithmetic. So there is a couple of integer instructions missing. And if you're kind of a code cracker or a code analyst, you will not find this chip very useful because it exactly lacks these intrinsics that you want to have, or even these assembly instructions that you want to have. It's mostly focused on floating point. Once more, the Sandy Bridge pipeline is exactly the same picture we had before. Here, these 3 ports are our AVX sections. We can do 1 multiplication, 1 addition, and 1 shuffle at one time. A shuffle is exactly what I will speak about in a couple of sections, and you will have the opportunity to try that out. So in principle, it could be three instructions that we dispatch at the same time. Okay, we have that. Little repetition from before. Nice thing about AVX is compared to earlier implementations is where we had 2 sources, that we now have 3 sources with a destination register. So you don't have to write one of your initial sources. So there's no need for an explicit copy. So we make the code a lot smaller than we actually did before. Okay. Now, to actually how do we program intrinsics? In order to specify a vector type, we have a couple of vector type symbols here that is Intel, I would say specific. It's of course also present in GCC. I don't know if it's, how do you deal with that in the Cray compiler? You don't? Okay, so you have to compile it with GCC or with ICC. Can you link to the Cray compiler then, or library or whatever? Yeah. Yeah, ABI is compatible. Yeah, good, okay. Okay, so there is 3 vector types. This underscore M256, that was the original vector type that dealing with floats, right? Then there is a vector type underscore M256D that deals with 4 elements of double, or an integer underscore M256I deals with 8 elements of a 32-bit integer. Right? There's a naming convention for intrinsics. You will find that there are many, many, many of these functions. The functions ending with underscore PD operate on packed doubles, meaning they operate on a full vector of the number of elements that it has. There might be PS, which is packed single, but there might also be things like EPI, which we're not interested at the moment, which deal with integers, right? Or even EPI 16 or stuff like that. So I'm not speaking about that currently. The only interesting thing I want to mention is we have this PD, but that we have also SD and SS. The SD and the SS deal with scalar double and scalar single. So you will only use the last or the first element of the vector to compute it. It's not a parallel execution, it's a scalar execution. It will deal with only one element of the vector. Okay, so how do we get information into the vectors? That's the first problem that you have, because you have all this fancy vector stuff, but on the other hand, you have arrays that reside somewhere in memory. So what do? So we need to load and store into vectors, and therefore we have a couple of routines, and we want to distinguish 2 of them. First, the aligned load, and then the unaligned load. The aligned load is just MM256, so this is a specification of the vector length. There is also 128, and in the future, or even on other architectures, there might also be 512. On Sandy Bridge is 256, so all the vector instructions should start with underscore MM256, then underscore what you want to do. In this case, load underscore a packed double. And what you hand it over is just the pointer to the array and the specific position you want to load from. So you want to load from, say, the 10th element. You would say array name, well, and array name, square bracket 10, will give you the pointer to the 10th element of the array, and then from there on it will load 4 doubles. Just straight what is written in the memory at that point. Storing is just vice versa. Underscore MM256 underscore store PD will store this vector A into the position pointer P. And there you can do the same trick. Right? In this uppercase here, I assumed that the position star P is aligned to 32-bit byte. So half a cache line, essentially. And this is the width of the vector. So this instruction will crash if it's not aligned. And you're invited to try that out when we do the hands-on later. Just try an unaligned load and a aligned load on an unaligned position and see what happens. Okay, so if the array is not aligned, we have this other set of 2 functions where it does exactly the same thing. It just says load U for load unaligned and store U for store unaligned. Why this alignment stuff? All right? So what it essentially does is we operate on cache lines internally. So we never load a single bit of memory somewhere. We always load a full cache line, and the cache line is 64 bits. So first of all, if we are not aligned to this cache line, to this 64 bits, we probably hang over the cache line at some point. So we need not 1, but 2 loads, because we load from two cache lines. Internally, that's called a split load and will cost you some. On the other hand, there is also performance benefit from loading from a given boundary. So if the boundary is basically, if you're on the boundary with respect to 32 bytes, we're loading fast. If we're not on the boundary with 32 bytes, we're loading slower at least. It's not so bad on Sandy Bridge anymore. It's still a performance impact. So in this case, this would be a load if we assume that this array A is aligned. If we shift it on off by one element, oh, I just forgot to change the vectors here, or the vector indices, then the load is unaligned, and we need to use load U instead of load. This is how we get this stuff into the vectors. In order to establish alignment, there is an underscore mm_malloc, the size of the aligned of the field you want to allocate, and then you put the alignment here. In the case of AVX, it has to be 32 bytes. In case of the mic architecture, it will be 64 bytes. Okay, this is how we get it into the vector. Okay. Then we have something written, like 4 elements of double from a given field, and we have it in a vector. What we do? Well, the most trivial thing we probably can do is doing arithmetic operations. And all of the arithmetic operations, well, most of them, will act on elements of these vectors, well, element by element, element-wise. Right? So if you execute this add operation on 2 vectors, one vector containing the elements of the field A, the other one of the field B, and you add them, you get a vector containing the sum of that. And it's just element by element, right? And this works for most of the operation. There are some exceptions, like horizontal add, which don't do that. What arithmetic operations are supported? This is addition, subtraction, multiplication, division, square root. There's a couple of others, like round, where you have a specifier which way of rounding you want to use. You have ceiling for divisions, where you want to go to the lower integer for the division, and floor, where you go for ceiling, where you go to the upper part of the next higher integer from the division, and the floor, where you go to the lower one, or minimum and maximum, where between 2 vectors you get the minimum or the maximum of the respective elements in the 2 vectors. This is kind of stuff you can do, but it's all element-wise. So you just do it bit by bit, and you will say, well, this is pretty useless because my algorithm requires something completely different. Because I want to add the fields, say, go back to a vector here. I want to add the fields A0 and B1. How do I do that? I need to do an unaligned load to get it in. No. And this is what intrinsics programming is most about, rearranging data. Because this is trivial. Once you have it in this form, it's easy. But to get it in the form is difficult, and usually the compiler should do the job for you, but sometimes it's just not possible. Okay, data rearrangements. So this would be all pretty inefficient because we would be not able to implement a real algorithm with these arithmetic instructions if we didn't have data rearrangement. Yeah. So the question is, what do we do if we need to load skew elements from an array somewhere, or if you want to distribute different elements across vectors? We need some particular instructions to do that, or operations to do that. And those operations are broadcasting, shuffling, permutation, and blending. And this is what the rest of this talk will be about. First of all, there's an operation that's called broadcasting. Broadcasting is usually what we do when we distribute one value across a whole vector. And this is usually in calculation, these are constants that are things that are constant over a given field. The intrinsics for doing that is _mm256 broadcast SD. Now it's a scalar double instruction. It will give you the full vector of that, but it's marked as SD because it just operates on this single value. And it will distribute the value in the pointer A, it's a memory address, by the way, into all the vector elements. There is also a similar operation that is called set1 PD that will distribute a double value, not a pointer anymore, a double value across the vector. So this is pretty easy. Now, coming to something completely different, we want to have mixes of two vectors. So you have two vectors that have fields that need to be mixed into a single vector. What do you do? And the appropriate operation for doing that is called a blend. By the way, there's a typo. It should be 256 underscore mm 256 underscore blend underscore PD. We'll choose fields from either vector 1 or vector 2 into the resulting vector. And you do this via a constant integer. And in the integer, in the dual representation or binary representation of the integer, where we find a 1, we take it. Do we have an example here? Yes. Where we find a 1, we take it from the second source. Where we find a 0, we take it from the first source. So these are some examples of how this is done. So if the control, once more, the syntax here, you have the arguments are vector 1, vector 2, and an integer, and the integer must be a constant. If the control value or this integer value is all zeros, then you take everything from the first source. If you have a 1 at the first position, then you take everything from the first source except the first value that you take from the second source. If you take the first and the third, and we read this from the end, of course, because this is a way how you read it, and you see the vectors are also ordered in this way. You take the first value from the second, and the third value from the second, and all the others from the first source. And this is how it is done. So you can mix two vectors. Basically, you can decide which parts you want to have. Now that is kind of useful, but sometimes you also need to flip positions of vectors. And therefore, there's a little bit more complicated instruction that is called a shuffle. A shuffle can change positions between two of these elements, not over a lane. The lane is basically what is left over from the previous SSE instruction set. So SSE was basically this size, and the lane divides these the lane boundary divides these two lanes, and we can't shuffle over the lane. So what we do is we actually shuffle in the lane. But you can choose either value 1 or value 0 or value 1 from the first, or 0 or 1 from the second source. So you can mix them and rearrange them in the same step. And you do that again via a constant integer select or control. And this is some example how it is done. Basically, this is the algorithm that is implemented. So if the immediate value, this control value, is 0, then the destination value, the first element of the destination value will be the first element of the first vector. If it is 1, it will be the second element of the first vector. This is pretty complicated. I have more visual examples. If the second binary position of the control value will be 0, then the second element of the destination vector will be the first element of the second source, or if this is a 1, it will be the second element of the second source. Now, this is all pretty complicated. Here are some examples, right? I called the vectors A, B, C, D, and E, F, G, H. And the control value 0 will take the first element of the first source, the first element of the second source, first element of the first source, the first element of the second source, yes. And the second lane, the first element of the first source, and the first element of the second source. First element of the first, first of the second. Works. And now we can play all these tricks with the stuff. Let's look at it. Oh, hello. Let's look at it in this perspective. These are some examples how you can shuffle, right? And you see now it's a little bit more, the lines here can cross. In our previous examples, we just had to put the second element always in the second element. Now we don't have to do that anymore. We can flip them around. By the way, this presentation is in this directory. You will probably need it for reference in the, during the programming. So, for example, let's take one. 0, 0, 0 we had already. We always take the first element, right? Take the first from the first source, first from the second source. Let's try all ones. This means take the second element from the second source, the first source, and the second element from the second source. So the second is B from the first source, put it here. And the second is F from the second source, put it in here, works. Right. So this is one way of rearranging. This is pretty tricky, and when you come to the examples, there are 2 shuffles required in the example we will program. And I gave the values right away, but it still is not completely obvious how to order this stuff. So you probably have to test out a little bit. Maybe you can try it and play around with it. This is a pretty powerful instruction, actually. Good. There is an additional assembly command that can do, or intrinsic, that can do basically the same thing, but it will do it with a single vector. I mean, if you look back at the shuffle, nobody forces you to use 2 different vector variables here. You can always use the same vector variable. But then what you should do is actually use this instruction, which is called underscore mm256, is missing here again, underscore permute underscore pd. And this will do the same kind of shuffling just from a single source. So the control value is basically the same. Right, so take the first element, take the second element here, take the first, take the second, and this is how the shuffling goes. If you do the zeros, you will do exactly the same as we did in the shuffle examples previous on. You will get, and you must envision the shuffle with 2 identical elements. You get the A here from the first. You would get the A from the second source, which we don't have here anymore because it just takes 1 argument, and you get an additional A here. So this is another way of reordering a vector. Particular example is just flipping these things cross is something that happens very often. We will come to that. You will find it absolutely obvious when we come to it.
May I sketch one example? So
yeah.
One example is complex arithmetics.
Yeah.
Where you have real, imaginary, and you need to sort all the reals into a vector register in all the imaginaries, and then apply a multiplication or an addition to, to get arithmetic in terms of complex numbers. And then you need to shuffle them back to realign them in real, imaginary. That's what you said.
It can be automatical by compiler. Sometimes the compiler recognizes. And my typical example, because this is what I'm most exposed to, is partial differential equations. Because if you write stencils, I don't know if you envision the stencil, it's basically, you have a zeros element, it depends on the neighbors, right? So if you think that in vectors, it will be the neighbors, but then they have a trailing tail to the right, in the direction of the memory. And then you have like this kind of shape there, and if you push it across, you see that the middle element contains, where we start, n plus 1, n plus 2, n plus 3, and the element above it starts with n minus 1, essentially. N minus 1, n plus 1, n plus 2. You push that together, and then you can do everything element-wise. Everything will be extremely fast. I mean, you can get to performances which are roughly 50-60% of the peak performance doing that, which is quite something, right? And if the stencil gets extensive, if it's a big stencil, like not say second order, we will do second order, but the usual case where we do that is order 8 to order 14th. So the stencils are big. in their approximation, then this gets extremely complicated, and the compiler won't understand it anymore. It will say it's not worth it vectorizing. And it will do a scalar version, and you get no performance whatsoever. So this is actually really cool stuff if we want to get to performance. But the thinking is pretty difficult, I agree. Like all this, this is completely boring, and you ask yourself, what's that good for, right? But it will be, I mean, once you come to think about it, it's absolutely obvious that, oh, of course, yeah, that's what it's good for. Because that was implemented for good reason. Okay, last but not least, cross-lane permutation. So everything we just did is all in lane. It's all within 128 bits because of this legacy of SSE that we have. Now, you will say, oh, that doesn't help very much because I need to bring this element, the first element of a vector, into the third position. And it just doesn't work because it's across the lane. So what you have to do is actually change, well, permute the lanes themselves and then do one of the other operations. There is an underscore MM256, sorry for that, it's missing again, permute 2F128, which will exactly do this. And it has, again, this control value that allows you to specify which lane you want to shift where. And I'll just show you some more visual examples from the second and from the first source. So you can, again, here use two sources. Generally, I do this with, because usually my intention is with that, I want to flip the lanes. So I do it with a single source. It doesn't mean you have to do it with a single source. You can have very fancy use cases where you have two sources. Let's look at that, how that works. Here it is done with elements again, of course, because a lane contains two elements. So the control value is now very complicated, and just to show you how it is calculated, this is how it is calculated. There might be fancy macros within our in our header file that do that a little bit more transparently, but I give you some useful values. So essentially, what you have to look for is in an 8-bit integer, the first and the zeros and the first and the fifth and the sixth, the fifth and the fourth and the fifth position. And you give this values from 0 to 1, meaning you have 3 values of choice for a given integer. Right? You have 2 of them. This is the bold positions here. And 0, 0 means first lane of first source. 0, 1 means second lane of first source. 1, 0 means first lane of second source. And 1, 1 means second lane of second source. And this is how it turns out. So if you do 0 all the way, it will give you the first lane across 2 lanes. So it will copy the first lane into 2 of the lanes. If you do a 3 in the position 4 and 5, it will, let me see, it will cross, no, it is identical, right? This is identity 48. It will copy the first lane into the first lane and will copy the second lane into the second lane. It's identity. It will change nothing. Then there is the first lane into the second lane. So the first pair into the second position, and from the second source, the first position into the first position. So this is basically only the first positions. And this guy is a lane flip. This is the most interesting part for me. This is the value 3. We take the first source, the first lane, so the first 2 elements, and put it in the second position. And from the second source, we take the second 2 elements and put it in the first position. And this is what usually I applied for. There's some examples with identical sources, which is some general use case. And again, you see that this is an interesting bit because it is from A, B, C, D, it changes it to B, A, D, C. And this is what people are often interested in, to flip the 2 lanes to do the same operation on the other combination of lanes. This is all for your reference because it's much nicer to look up these combinations because it make much more sense, actually. Okay. Also for your reference, the detailed calculation of this constant, because you can do more fancy things by actually setting parts of the value of the lane to 0.